can use the process of calculus to find the length of a curve on a plane that's a rectifiable curve, and using our applications of our derivatives and our integrals to find this length. So here it says for the length of a curve, a rectifiable curve is a curve that has finite length. So it's something that we can find the length of. And a sufficient condition for a rectifiable curve is that the first derivative of the function is continuous on the closed interval that you're trying to find the length of that curve. Now, for our example, we want to find the length of the function f of x equal to x to the fourth over 8 plus 1 over 4x squared on the closed interval from 1 to 2. Just as some background of how we come up with the formula and what the formula is that we use in order to find our lengths of a rectifiable curves on the plane. Suppose we have this curve that we want to find the length of. If I take and cut the interval over which we are finding the length into subintervals, and I look at the little subinterval places, spans across here, where this is my first point, and then that subinterval ends, and I have another point on the curve, etc. throughout. So here is the ordered pair x sub 0, y sub 0, the ordered pair x sub 1, y sub 1, the ordered pair x sub 2, y sub 2, x sub 3, y sub 3, etc. throughout. And at each point, so from one point to the next, I'm going to draw horizontally across and vertically up and make a right triangle. Now, if you look at the hypotenuse of the right triangle at each of these, the hypotenuse of the right triangle very closely follows an approximation for the curve length right in that little spot. And if I take these closer and closer and closer together, I get better and better approximations to the length of the curve for a fixed number of subintervals. So we're going to use small case s is our notation for our length of a curve, is approximately equal to the summation. So we're going to add up all of these little spans of the hypotenuse for each of those right triangles throughout the whole thing. So I equal 1 to n of, remember, for a Pythagorean theorem, we have that the legs squared, so our horizontal run squared, plus the square of the vertical is going to be the square of the hypotenuse. So if I take the square of the horizontal component plus the square of the vertical component, that gives me the square of the hypotenuse. So we're going to take the square root to get the length of each of the hypotenuse throughout all of those subintervals. Now, that's where we're going to start off, but that doesn't lend us to have a formula or an operation that gives us the actual length of the curve yet. Now, what we're going to do next is, and we can do this for either of the delta differences, whether it's the delta x sub i's or the delta y sub i's. We're going to do our example with the delta x sub i's. So I'm going to take and factor out a delta x sub I squared underneath the radical. So if I factor it out, delta x sub I squared divided by delta x sub I squared is 1, plus delta y sub I squared divided by delta x sub I squared gives me that fraction. And I close that off, and then I factored out the delta x sub I squared, so I write that afterwards. I just factored it out of each term, but it's still under the radical. Now, the square root of a product is the product of the square roots. So I'm going to keep this first one as the square root of 1 plus the delta y sub I squared over the delta x sub I squared, but since they're both squared in a fraction, I can write that as the fraction quantity squared. And then I'm going to take the square root of delta x sub I squared, and that's just delta x sub I. So you notice from here to here, I took the square root of it, and then I also wrote that overall as a fraction. Now, that just gives me an approximation of the length of the curve, and I'm trying to get to a formula that would actually give me the length of the curve. So if I take the limit as the norm of the partition approaches 0, so remember, I don't necessarily have to have equal subintervals as long as each partition I find seek out the largest spacing at that point in time and make that spacing smaller. So the norm of the partition, the limit is the norm of the partition approaches 0. Of this summation, I equal 1 to n of the square root of 1 plus y sub I, delta y sub I over delta x sub I, quantity squared. Out of the radical is your delta x sub I. Now, from the mean value theorem, I have that if you've got that continuous function on the closed interval, then you have that for some c in that interval, there's an x value where the derivative of that function is equal to the slope of the tangent, or slope of the line connecting the endpoints of that interval. And so I have our derivative is continuous because it's a rectifiable curve. So by the mean value theorem, I can make the assumption or make the connection that this limit is going to be the definite integral from a to b of the square root of 1 plus f prime of x quantity squared and then dx for the delta x sub I. So that's if I would have gone up here and divided everything through by a delta x sub I squared. Now if I would have factored out the delta y sub I quantity squared instead, and then looked at it, I would then have my other formula, which is in terms of a function where x is equal to a function in y instead of y being a function in x. And if that's the case, then your endpoints of your interval are going to be the y coordinates along the span. So those are the two formulas that we can use for our length of our curve. So here for our example then, we want to find the length of this function, and it's y equals an expression in x's, so it's going to be the first one that we developed, on that closed interval from 1 to 2. So from the formula, my length of the curve is the definite integral from 1 to 2 of the square root of 1 plus, and I need to take the derivative of my function and square it, and dx. Now our function is better suited to take the derivative if I rewrite it as 1/8 x to the 4th plus 1/4 x to the negative 2. Remember that exponent is just on the x, so when I write 1 over 4x squared as a coefficient times a variable to a power, it's 1/4 x to the negative 2. Now our derivative, f prime of x, bring the exponent down, multiply to the coefficient that's in front of it, and then subtract 1 from the exponent when it's letter-based to number power. So this will be 1/2, 4/8 is 1/2, x to the 4 subtract 1 is 3rd power. And then when I bring down the exponent of negative 2 and multiply it to 1/4, that'll be negative 2/4 or negative 1/2. X to the negative 2 subtract 1 is negative 3. So that's my derivative. So that's what goes in this quantity that is being squared in our formula. Now this I need to do some work on to get it ready to integrate it. I don't have any outside factors that I can use as a u substitution, so what I need to do is to multiply out this binomial, combine like terms, and see what we have. Well, if I take this 1/2 x to the 3rd minus 1/2 x to the negative 3 power times itself, because we're squaring it, then that's going to give me 1/4 x to the 6th. Now I'm going to get a negative 1/4, and x to the 3rd times x to the negative 3rd is x to the 0. So I'm actually going to get a negative 1/4 x to the 0, which is just negative 1/4 for the outer terms. And then for the inner terms, again, I get negative 1/2 times positive 1/2 is negative 1/4. X to the negative 3 times x to the positive 3 is x to the 0. So that just gives me a negative 1/4. And then negative 1/2 x to the negative 3 times negative 1/2 x to the negative 3 is positive 1/4 x to the, keep the base, add the exponents. Negative 3 plus negative 3 is negative 6. So that gives me a positive 1/4 x to the negative 6. So then simplifying this gives me 1/4 x to the 6th minus negative 1/4 minus 1/4 is negative 1/2. And then plus 1/4 x to the negative 6. Now when I put that into my formula, in the spot that it goes, so it's 1 plus that expression, 1/4 x to the 6th minus 1/2 plus 1/4 x to the 6th, and then dx. Now combine your like terms. That's going to be the square root of, well, 1 minus 1/2 is plus 1/2. So I have 1/4 x to the 6th plus 1/2 plus 1/4 x to the negative 6. And then dx. Now, here's the thing that you want to recognize. Look at this expression that's under the radical. Look at the expression that we got when we multiplied out these two identical binomials. So when I had 1/2 x to the 3rd minus 1/2 x to the negative 3rd times itself, when I did the inners and the outers, the variables were common factors that removed, and I just got my negative 1/4 and negative 1/4, which gave me a negative 1/2 in the middle. And then I had my 1/2 x to the 3rd times 1/2 x to the 3rd was that 1/4 x to the 6th. And then the negative 1/2 x to the negative 3 times the negative 1/2 x to the negative 3 was the positive 1/4 x to the negative 6. I have almost the exact same thing here, except that has a minus 1/2 in the middle term. This has a plus 1/2 in the middle term. So actually this factors, and this factors as two identical binomials. This factors as 1/2 x to the 3rd plus 1/2 x to the negative power of 3 quantity squared, dx. So it factors to almost exactly what you had there, only with a plus in between instead of a minus in between to get this plus 1/2 in the middle. And if you were to multiply those out, you would see that that multiplied out gives you that. So now I'm taking the square root of a quantity squared. Well, that's just the quantity. Okay, so since I have it where I just have that expression, now I can actually integrate this term by term. So when I integrate, remember letter base to number power. To integrate, you add 1 to the exponent and divide by that. So add 1 to 3, you get 4, and divide by that gives you 1/8 x to the 4th. Now add 1 to negative 3, you get negative 2. And when you divide by negative 2, you're going to get a negative 1/4 x to the negative 2. And you're evaluating that from 1 to 2. And then plug in the 2 minus plug in the 1. So I have 1/8 times 2 to the 4th minus 1/4, and x to the negative 2, you can put it back down in the denominator so it's easier to calculate when you plug the number in it. So that would be an x squared in the denominator. When I put in the 2, that'll be a 2 squared in the denominator. And then minus putting in the 1. So that's 1/8 times 1 to the 4th. And then minus 1/4 times 1 squared. And when you go through and work out the calculations for that, you'll get the length of the curve is 33/16. So whatever the unit measurements are in terms of the region that you're graphing, the plane that you're graphing that function over, the length of that curve is 33/16 units long.